Next is Sascha Von Meier from CIEE talking about the DOE-funded Micro-Synchrophasor project.
Thank you, Therese. Can you hear me okay? So do we have a hard stop at 4? I don't think so. Okay. I will stick to less than 20 minutes. All right. So thank you. I think some of you have probably heard me talk about this project before, but I will give some overview and background and some pictures of recent accomplishments. The problem that we're looking at is that in power distribution systems, as a perfect segue really, it's very difficult for utilities and operators to see what's going on. There are instrumentation technologies, including new ones like synchrophasors being installed all over transmission systems. That covers the high voltage part down to the substation typically. Then we have smart meters and all manner of smart devices at the building level. But in between, at the medium voltage distribution infrastructure, just where you want to identify the health of those cables, for instance, there's really not much in the way of sensing that provides situational awareness for those operating the system. And that was never a problem when the distribution system consisted of passive items that you weren't trying to control. Really, the goal was to avoid overloads and to make sure the protection was safe and effective. But in order to actively manage distributed energy resources from distributed generation to storage, vehicle charging, controllable loads, and so forth, there really is a need to be able to see more what is electrically happening on those circuits. So the concept that's the topic of this work is to essentially skip a generation of technology and go straight to the state-of-the-art of synchrophasor measurements that offer a very highly refined approach to measuring the electrical conditions, and to network them in a way that makes sense so as to provide actionable operational intelligence about distribution resources. So we are about halfway into an ARPA-E-funded project here at Berkeley with Lawrence Berkeley Lab. Colleagues from the engineering department, Kameshwar Pula, David Culler, and Sila Kilichote at Lawrence Berkeley Lab is involved, and CIEE is coordinating this effort. We're also partnering with private company Power Standards Lab, which has developed a new device that's tailored to distribution measurements. Before I get into the capabilities of the device, let me give you sort of a general overview of the objectives here. We're trying to develop a network of these high-precision phasor measurement units, we're calling Micro-PMUs, to measure voltage phase angle, that is the precise timing of the voltage waveform, along with voltage and current magnitudes and current angles, to within a level of accuracy that has not been done because it's not necessary to do in the transmission context. And we're trying to understand fundamentally what is the value of making this measurement? What could you use it for if you had it relatively affordable and accessible? What new kinds of insights can you get from that? So part of our project is about hands-on deployment, and part of it is really a theoretical exploration of applications for these types of data. So we have been looking at the requirements for different kinds of diagnostic and control applications. What could you do with synchrophasor measurements? How good would those measurements have to be? How quickly would you have to get them? And there's a list of applications that actually a much longer list that you might have heard me speak about a year ago, and we have since been narrowing them down to some applications I will come to at the end. What's really important here, and I want to cover the basics in case people are not familiar with the notion of synchrophasors, it is really a fundamentally different kind of measurement. When we're talking about alternating current or alternating voltage, to a first approximation, we imagine everything on the AC network, which for us really means the whole western United States, from Washington down to Mexico, from Canada, in fact, down to Mexico, all being in step, being synchronous. But in fact, there is a really important shift that's labeled little red delta in the graph. That's a time shift between the voltage waveform at different locations. And that little delta is absolutely essential for the AC power flow along a transmission line and also along a distribution line, although the delta is going to be a lot smaller. This approximation that you're seeing there is an okay approximation for transmission systems, where the real power transferred goes approximately as the sine of that little angle delta, and the product of the voltages at either end divided by x, the reactance of the transmission line in between. Now, to measure this was not possible until we had GPS satellites and a precise time reference that you could share between different locations. Because clearly you need to agree on exactly what time it is between two locations when you're measuring the voltage crossing zero or reaching its maximum, so that you can actually measure that shift. Before, the first synchrophasors were used in transmission systems in the 1990s. There were models that calculated these phase angles, but you couldn't really measure them empirically out in the field. The accuracy to which you can measure that phase shift, of course, depends on how good your clock is and your agreement at different locations about that clock. So what we're shooting for here, because the deltas are very small, down to less than 1/10 of a degree, we're looking at the microsecond realm, really, of synchronizing and comparing measurements. So measurements are time-stamped at different locations and then compared. So Power Standards Lab is building on their already commercial P-Cube power quality instrument, adding a high-precision GPS receiver to be able to make that time stamping and measure the voltage phase angles, in addition to, of course, the voltage magnitudes and the currents. So the resolution, the target resolution is 10 millidegrees, which is really very precise. Typically at the transmission level, about a degree or so of accuracy is okay for the kinds of power flows that you're interested in and the kinds of phase shifts which can be in the tens of degrees between location. And then these devices can communicate. You can plug them into the internet. What we're demonstrating here is a communication network using 4G wireless service. So this picture actually is from the Grizzly substation up the hill that's powering us right now. And up there on the roof, you see the GPS receiver, and you see the little antennas from the modem, the cradle point modem. And Verizon is helping us transfer many, many data points. In fact, 120 samples per second for each channel for each device, down to the Quasar server here in Soda Hall, where David Culler and Michael Anderson are concatenating the data and presenting them for us. The project is really ambitious in terms of the field installation. So we've been working with a number of utilities that include Southern California Edison, SMUD up in Sacramento, the Southern Company, and then also with the UC San Diego campus where they have the microgrid. That's a very interesting research playground to put these. And we're right now in the process of planning these deployments, which we have learned over the past year up at LBNL at our pilot site and here on campus that, of course, the installation is always more complicated than you thought. And there's little details such as you don't really want to drill holes in the roof, so we had to design this magnetic mounting plate that you see is supporting the GPS receiver up there. And many details also because you have to work with the field crews who, or facilities services in this case, who are authorized and safe to go near some of these 12 kilovolt equipment to make the installation. So we have right now 6 PMUs, 3 more awaiting installation, we hope actually within the next week or so. and reporting to the server. We're also talking with the utilities, poring over circuit maps like these, and talking about strategically where would be the best locations to instrument, which turns out are the locations that are electrically interesting, but also the ones where it's, in practical terms, feasible to make the installation and not too expensive. I think it's very important to keep those kinds of practical constraints in mind, because as we're trying to support the commercialization of this technology, we know that for electric utilities, it will make all the difference in the world if it's something that's straightforward to install. So because the device has voltage inputs between 100 and 690 volts, it requires a potential transformer to be there if we're sensing a voltage, for instance, at the 12 kilovolt level. So we like to go in places where there's already a transformer there. We don't have to attach a new one. So just to show you some data, here's just a kind of incident that's cute, because we could see that in the Oakland Hills there was an outage and there was a voltage blip that could be seen in other places. The really great thing, and David Culler and Michael Anderson should be presenting this, or at least receiving applause for it, because they've done amazing work here. They're at a conference this week. But so they have built a visualization tool in response to the question, can you help us figure out what these data mean? We don't really know yet how we want to consume these data, because no one's looked at these synchrophasor data at distribution, on distribution systems before. So we kind of want to pore over them and, you know, zoom in and out in time. We don't really know yet exactly what we're looking for. Could you just, you know, build for us a visualization tool with unprecedented power and flexibility? And I said, okay. And so here are just some screenshots. This is an actual phase angle difference between two locations at the pilot site. So we're looking at, you know, angle separations on the order of, you know, some hundredths of a degree, very small. And I can't promise you yet that this is really going to be meaningful and useful, but we think so. What's cool here is you see that it's actually showing you a statistical abstract of a larger period of time, because this tool, as I'll try to show you live, but I wanted to have the screenshots in here just to be sure. As you're zooming in, you see some oscillations. I don't know yet what these mean, so don't ask me that. But as you zoom in, now we're getting to 120 samples per second. And what's also really cool is that this tool will show you how many data points are actually being represented per pixel. Okay, so here's, let me live dangerously and go to this link and see. So this is what happens is when you create a permalink from a graph that you happen to find, and you say, okay, this is a cool sequence. Let me, you know, take a snapshot of this and send it to my colleagues to see if they can figure out what's happening here. So what we have in this particular picture are I just chose a current and a voltage measurement. But now the exciting thing, or let me show you, when I highlight this stream, it will show you that actually each pixel on the screen here now represents 66,000 measurements, right? And the power lies in the fact that as I scroll, and now I can, you can go down to the very granular level. So this is pretty exciting, because essentially, when you know how to use your mouse properly, the visualization tool will help you zoom in and out very seamlessly from fractions of a second out to days and weeks and months, which is a wonderful feature, especially when you're when you don't know ahead of time what are going to be the interesting observations that are really going to be worth recording and analyzing. What we have come down to, the narrowing down the applications, is first of all to validate the circuit models on which we're measuring. Next is to do topology detection, that is to be able to see what switches are open and closed in the network, to estimate the operating state of the network, and then to be able to characterize more specifically the behavior of loads and distributed generation on on a higher granularity than is possible with conventional measurements. And actually, one comment I want to add here is that the timestamping, the accuracy of the timestamping, really has sort of a secondary value. It's absolutely necessary to even begin to measure a voltage phase angle. But there is a benefit even in the timestamping approximately, and approximately I mean not necessarily to the microsecond, but to within some fraction of a second of measurements at different locations, because that's something that really is not available in distribution systems right now. Some of the utility, the conventional SCADA data and other kinds of instrumentation, often the time steps are not only crude, but they're misaligned. So you really can't track a phenomenon between and across different locations and say this is the same event that happened, and look for causal relationships. So the time synchronization in and of itself is a really important factor here, and that allows us to take a new look at how the steady state and also dynamic behaviors of variable generation and loads are going to influence power flows and each other potentially. The approximations that work for the transmission system are wrong in distribution, because in transmission you assume that the resistance of a line is very small compared to the inductive reactance. That's wrong in distribution, which makes the math entirely more complicated. The math also becomes even more complicated because you have three phases that are not all behaving the same way as one assumes in transmission. So these are still approximations. The good news is that by measuring the voltage angle in addition to the magnitude, you can deduce real and reactive power flows in a way that measuring magnitude alone doesn't let you do. So if we look at this sort of in a schematic framework, measuring the phasor at a particular node can tell you about power flows from points on other branches of the network that you're not directly touching. So for instance, if I'm looking at the difference in the voltage phasor between V0 and V1, I can see something about what P2 is doing, what the other generator is doing, because it will affect that phasor profile along the circuit. The first thing that we're working on up at LBNL is to validate that the maps, the circuit maps that say what kind of cable there is, agree with the measurements. And that's been exciting. We happen to choose a particularly difficult stretch of model to validate. If we had only known that, you know, a short section of underground cable that's very lightly loaded and behaves in a capacitive way is really not the easiest place to start with getting all the currents and voltages to make sense together. But we're getting some happy answers. There is the topology detection is something that's really of practical importance to utilities, because they don't always know that they can trust the status of switches being open or closed at different points. And actually starting with phase identification, many utilities aren't really sure what's hooked up to phase A, B, or C. So that is also those are algorithms that we're working on interpreting the kinds of measurements I showed you to see if it's plausible for voltages and currents on phases A, B, and C to be aligned, or are they mislabeled or misaligned, for instance. And then a safety-relevant observation is if there's a power island. Certainly you can detect that by measuring the phasor on either side of that open switch, that open breaker. State estimation is an ambitious goal, that is to be able to identify the voltage phasor at each node without actually instrumenting each node. Strictly speaking, that can't be done, but you can fake it, because you can draw some conclusions from pseudo measurements. We have actually some papers published on combining a handful of highly precise synchrophasor measurements with a big handful of not so precise meter data from different locations, and looking at how do we minimize the error and how do we bring that knowledge together and estimate with the best degree of confidence what's actually happening at any one instant. So really this theme here is that we want to substitute a precise empirical measurement in real time for a good knowledge of the model of the network, which often is not available. And when it comes to control strategies, what we think is useful to pursue here with the benefit of these kinds of measurement are strategies that don't rely on a very good circuit model in order to optimize, because any kind of optimization means that you have to have good knowledge of the network that you're trying to optimize, and you need information about different sources, different participants, and what they're doing. So it means a lot of communication and good input data, which we don't think that in practice are often available. So this approach here of non-model-based control is to say, can we identify a useful way to control a resource, such as something that's injecting power P1, that could modulate its performance based on a measurement of only its own phasor and one other, say at the substation. And, for example, hold that phase difference constant or respond to that phase difference. So how useful could that contribution be for modulating, controlling, and perhaps just flattening the power flow profile in the network? So these are things we're still exploring. In general, whether we do it or someone else does it, to build on this work, I believe that the direct observation of these phasors is going to enable a new level of situational awareness for system operators. That is going to mean faster service restoration, better management of extreme events, better understanding of unintended impacts of distributed resources, and ultimately, rather than worrying about adverse impact, being able to more effectively recruit these distributed resources to provide beneficial services to the grid. So that really is the paradigm shift from the passive to the actively managed distribution systems that we hope will be enabled by having that new level of visibility.
Is there a quick question for Sascha?
Try to make it quick. Thank you very much. I've heard about this project so much, and it's really nice to see it, what it's really about. I was wondering, so we know now that it's bad to have a large delta. I guess that's the gist of it, right? But what can we do if we detect that there is a shift in phase angle? Is there any approaches that the utilities companies currently take to actually get rid of that shift, or what do they do about it?
So we have to distinguish between the shift that needs to be there in order to facilitate the power flow. So there's a kind of steady state shift. I mean, in fact, it also changes dynamically, but there's a shift that's associated with power flow. So the shift in and of itself is not a bad thing. But what we're looking for is a way to measure changes in that phasor that are going to be diagnostic and that tell us about problems. And the problem isn't with that angle, but it tells us about something else that's happening. So, for example, in the state estimation, really the practical question that would be of interest to utility is, do they have reverse power flow on their network? Now, that reverse power flow may or may not be a problem, depending on the coordination of the circuit breakers, the protection system. In some cases, you might say that there really is an operational constraint that says we don't want a certain amount of real or reactive power flowing in one direction or the other. And so the phasor measurement gives you a very direct way and dependable way to see which way that's going. So it's really about distinguishing the everyday measurements that just tell you about the status of the system from the things that have become actionable, because you say we're moving toward a constraint violation, so we want to take some action to prevent it. It could be curtailing distributed generation, or dispatching storage resources, or some other method.
I have a quick question. I'm just kind of wondering, from a cost perspective, what the trade-offs would be with increasing the telemetry on substations and other levels deeper into the distribution system, and your synchrophaser project, and then what might be the coordination between those two efforts, cost-wise?
You know, I think that in terms of comparing the cost of individual sensors, right, you could say, well, the synchrophasors are on the order of a few $1,000s. Typically, you know, you might get other sensors for that much, or in some cases for a lot more. I think really the cost comparison is not so much a matter of comparing the individual sensing devices, but looking at the performance of the whole network and the integration of the information. Because I think what you're really after is some way to gather intelligence from different kinds of sources. You're not going to just take out your old SCADA system and replace it with synchrophasors. What you want to do is you want to leverage the investment that you've already made, for instance, also in smart meters. And ultimately, I think what is needed is a platform that allows you to bring together and combine information from those different sources. So it's really not going to be a trade-off of which sensor paradigm you follow, but it's going to be how do you best incorporate and combine different sources of measurements. Does that make sense?
Yeah. And the reason why I asked is because at least back 10 years ago when I was working for a utility, there really was no SCADA system. Mm-hmm. And so I'm just wondering, you know, in terms of what's the best bang for the buck, mm-hmm. in terms of getting better visibility into the distribution system, is it adding different telemetry, or could this maybe be a lower cost solution?
I think that the jury's still out. I think it could be a lower cost solution if we prove, and we haven't proven this yet, if we prove that having a very accurate and refined measurement and comprehensive measurement that includes the angle as well as the magnitudes, that substitutes for a larger number of sensors, of conventional sensors that you would otherwise have to deploy, right? Because each installation has its own costs of labor and design and stuff that we're learning about why it costs more and takes longer to get the sensors in place, right? So if you can get the same information about what's happening on the circuit from a smaller number of nodes, then that in principle should be useful. And we haven't proven that yet. But the intuition says that if you get a better measurement from one point, then maybe you could forego putting 3 others there.
Okay, thank you, Sascha.